Okay, so today we're going to continue with Chapter 12, which we talk about the basics of op-amp operations, and we are introducing the concept of negative feedback. And this actually makes the op-amp useful. Remember the four properties of an ideal op-amp are infinite gain, infinite bandwidth, infinite input impedance and zero output impedance, and those are all well and good things that we want from our amplifier, but practical op amps don't have all those things. They're all limited on all of those. In other words, they don't have infinite bandwidth and they don't have infinite gain, although the gain is really, really high. 200,000 is the example we've been using. 200,000 is not practical, however, because if you put a half a volt into an op amp, 200,000, that's 100,000 volts. You're not going to want to do that. It's very dangerous and it's impractical. So we add negative feedback in order to control the gain, and we also can control the bandwidth and the input and output impedance. So it gives us control over the op amp parameters. Now remember, an input of an op amp is two inputs, the inverting input and the non-inverting input, so the plus and the minus, or minus and plus in that order. And it amplifies the difference between those two terminals. So if you have 0 volts between the two terminals, you don't get anything out on the output. And we're talking about open loop gain. It's whatever the that 200,000, for example, would be the open loop gain. Now, when we add negative feedback, we take some of the output voltage and feed it back to the negative or the inverting terminal. And understand what that will do is if, like, for example, this input voltage rises a little bit, okay, that's going to cause the output to rise a little bit, and then that gets fed back to the inverting input, causing it to rise a little bit and kind of zeroing out the difference between the two inputs, and therefore it cools the jets, if you will, on the output. So it's a control loop. It's kind of like the cruise control in your car or a thermostat in your air conditioning system. You know, the air conditioner kicks on, cools the house down, thermostat detects that, turns off the air conditioner, and so on. So it's just the same principle. It's a negative feedback loop. So the non-inverting amplifier, we feed the input into the non-inverting terminal. And then the feedback goes again to the inverting terminal. Now there's feedback attenuation here, where we feed back a portion of that output. Okay, so not all of it. In this particular example, we only feed back some of it. So there's a voltage divider here. So what does that mean? What that means is this output is going, since these two inputs need to be equal, right, or almost equal to produce an output. All right, when everything's stable, basically we have these two inputs that are right next to each other. They're almost the same voltage. But we have this open loop gain of, let's say, 200,000. So they're almost equal, but just maybe a small voltage apart from one another. And that times that 200,000 produces your output voltage. This feedback circuit feeds back just a portion of that output voltage. So what that means is the output has to rise a certain amount to equal this input, and it has to compensate for this voltage divider. Okay, so if you're putting a volt in here, let's say, just as an example, okay, and this voltage divider is half, you know, only feeds back half the voltage, then the output's going to have to rise to 2 volts to produce 1 volt here on VF in order to make these two equal. Now right here I want to tell you that the best way to determine whether an op amp is working or not is to measure the voltages on the inverting and non-inverting input. If those are equal, then your op-amp's probably okay. If they're not equal, or almost equal, then you're probably missing some feedback. One of these resistors is bad, or the connection's bad, or both. Okay, so in the lab we often do that with some voltmeters. We'll look at a voltmeter and measure the voltage there and there and determine whether or not the op-amp's any good. So as I was saying here, it forces VF, which is the feedback voltage, to be equal to VN. VN is across RI here. Okay, in basic algebra, you can do some KVL here and determine that the closed loop non-inverting gain, that's what A sub CLNI, is 1 plus RF over RI. Okay. So if you want a gain of 2 of ACL, that would mean that RF equals RI. So you could put 10K here and 10K there. So 1 plus 10K divided by 10K that's 1, so 1 plus 1 is 2, so the gain would be 2. If you want a gain of 10, then the ratio of RF over RI would have to be 9. 9 plus 1 is 10, so that might be 9K. RF would be 9K, RI would be 1K, for example. So that's how you make these op-amps produce an amplified voltage. Then one example was gain of 2, the other was gain of 10. You can even have a gain of 100. And so we're going to determine the gain of this, a non-inverting amplifier. There's the equation, and 8.2 or 82K divided by 3.3K, and you get 25.8. So this apparently is 24.8, this quotient here, and plus 1. A special case is when the feedback RF is 0, meaning it's a short, okay, and RI is missing, it's an open, all right? So what you end up with is RF over RI. RI is infinite, so it produces, let me go back to this equation here. RI is 0, RI is infinite, so this expression here becomes 0. So the closed loop gain is just 1. So that's just a voltage buffer right there. All right, and what happens is, so input equals output. So what good is that? What's the difference between doing this and just putting a wire in here? Well, what you get is that the input impedance of this op-amp is really high. So it basically isolates the input from the output, and you get a nice current drive because the output impedance is low. So it's a current booster, and this is used all the time, okay? And that's what this says here. It avoids loading effects on input. So you hook a microphone up here, it doesn't even see the output. So there's the other configuration is the inverting amplifier, and that's where the input is applied through this feedback network to the inverting input of the op-amp. And here's your feedback. Feedback still goes through RF back to the inverting input. Okay, but we also feed the input through this resistor, and the equation is minus RF over RI, and that's for the closed loop inverting gain. Now we call this virtual ground, this node here on the inverting input, because as we said before, when the op-amp's working properly, these two terminals are about the same voltage, so this is essentially ground, because the non-inverting terminal is ground. So that balances them out, and so this ends up being 0 volts, which is virtual ground. And we'll do another equation here, another example. Closed loop gain is minus RF over RI, so 8.2 over 3.3 is minus 24.8. Now, the minus sign indicates inversion. What that means is if you put a positive voltage at the input, you're going to get a negative voltage on the output. So if you put 1 volt here, how many volts you get on the output? Minus 24.8 volts. So that's why these op amps have a plus and minus power supply. They have plus 12 volts and minus 12 volts. Okay, now for that example, you couldn't get minus 24.8 volts out of here because my minus power supply is only minus 12 volts. So you'd have to increase that or decrease your input voltage in order for it to work properly. You can only get as much voltage output as you've got on your power supply. Okay, this is what happens to the impedances. So the input impedance for the non-inverting input is increased by the open loop gain times the attenuation feedback, the feedback attenuation, which is this expression here. But this is always a number that is larger than or much smaller than the attenuation or the open loop gain. Like this is 200,000. So the input impedance increases dramatically and is generally assumed to be infinite. It's okay to assume that it's infinite for all of our calculations and our analyses. It's not. It's in the megohms or many hundreds of megohms, but for all practical purposes, it's infinite. Okay. Now the output impedance is actually lowered when you add feedback. So it's moving everything in the right direction when you add feedback to your op amp. You're increasing the input impedance and you're lowering the output impedance. Okay, and generally we assume it to be zero. That assumption works sometimes, sometimes not. And for the inverting amplifier, the input impedance is just the input resistor. And the output impedance is exactly the same as in the non-inverting case. Why is the input impedance equal to the input resistor in an inverting amplifier? Well, let's go back, if I can make this work. Let's go back. You notice this is virtual ground right here, this inverting input, right? So that's zero volts. And there's no current going into this terminal, the inverting terminal, because it's infinite input impedance. So you can see then that the input impedance is going to be this resistor connected to ground, virtual ground. So that's why the input impedance is equal to that resistor for the inverting case, right here. Yeah, and the output impedance is the same for both. There's some homework questions on this that you can practice. Some good examples in the text as well. I recommend you do all of those to prepare for the exam in a few weeks, okay? Okay, now, last week we talked a little bit about bias currents. There is currents that go into these terminals. They're small, all right? I mean, they're not. It's not infinite input impedance really. So we have to pay attention. But what can happen is if they're unbalanced, you can get an offset voltage out here. Okay. So what we do is we usually add a resistor to the non-inverting input. When that resistor is a series resistor, in this case, in the inverting case, it goes to ground. In the non-inverting case, it's in series with the source. And that resistor is equal to the parallel combination of the two resistors here, the input resistor and the feedback resistor. All right? Very common to do that. So for example, if you have 10K here for the RF and 10K for RI, well, 10K in parallel with 10K is what? 5K. So you put a 5K resistor right here. Okay, we say an ideal op amp has infinite bandwidth. Well, a practical op amp does not. Oftentimes it's a single pole situation, meaning it's minus 20 dB per decade after the critical frequency. All right, these are called compensated op amps. Not sure why they're called compensated. They seem to be decompensated, but that's what the expression is. So this is an example of one that has a critical frequency of 10 hertz, pretty low, and there's a 20 dB per decade roll-off. And notice this spot right here. at some point, and this is open loop gain, right? This is open loop. That means there's no feedback resistors. It's just the two terminals being driven. Now there's a point at which that gain drops to 1, or to 0, I should say. Unity gain, 0 dB, meaning 1, a gain of 1. Yeah, an op-amp, practical op-amp cannot operate up to light frequencies, if you will. There is a point at which it says, forget it, I'm not going to pass this frequency anymore, because there's filters in there. There's unintentional filters, if you will. They're made of transistors, and all transistors, as we learned in semiconductors, have it's like a sandwich. It has plates. The P and P junctions act as capacitors, so they do lose their gain after a certain frequency. And that frequency is called a unity gain frequency for an op-amp. Now the good news is that when we add feedback, which is called, we now have, instead of open loop gain, we have closed loop gain, okay? We have a manageable gain now. Instead of 200,000, it's 100. That drops down your closed loop cutoff frequency as well. It brings that in, okay? Now it turns out, okay, and here's this closed loop is the open loop times this expression here, okay? So we've actually, this cutoff frequency that was here for the open loop has gone out to this point here. So the gain that we choose stays constant out to a much higher frequency, okay? Even though the gain is lower, okay, it's more manageable, and it stays constant out to this new cutoff frequency. Instead of 10 hertz, it might be megahertz or 100 kilohertz or something. So that's better. And there's an expression, let's see. Let me finish this. So you can achieve a higher bandwidth by accepting less gain. So less gain, higher bandwidth. Now less gain is good. You say, you know, well, I want more gain. Well, you kind of do, but you kind of don't, because like I said before, 200,000 is not usable. Maybe 1,000's better, and you get more bandwidth as a result. Now, there's an equation here that the closed loop gain times the closed loop frequency response equals the open loop gain times the open loop frequency response. That's the gain bandwidth product, this expression here, gain bandwidth product. It's also equal to the unity gain frequency, which is FT. So that's ACL times FCCL, where FT is the unity gain bandwidth. So all these things are equal. These are constant, okay, which is very handy. So if you have a unity gain bandwidth for 741 of 1 megahertz, what's the bandwidth closed loop of the amplifier? Well, for this case, 82K divided by 3.3 plus 1 is 25.8. That's the previous example. What do we get? 1 megahertz divided by 25.8. We now have 38.8 kilohertz. Okay? So that's a much more practical number. Okay, well that's it for today. It's a lot of information for you to soak in. So do the homeworks. There's some good examples in the textbook. I recommend you do all of those. Also start putting together an equation sheet. Write down these equations. This closed loop gain equation, for the non-inverting op-amp. Write down the inverting op-amp gain equation, which would be minus RF over RI. Write down this equation and use all of these equations off of your equation sheet to do the examples in the textbook and your homeworks. That's the best way to prepare for an exam, okay? So when you do the exam, you'll have your equation sheet right there, and you can use it to solve the problems very quickly because you already have. You've done it using, you've solved the examples, and you've also done your homework with that. So I highly recommend you do that, okay? If you have any questions about what we talked about, please just post them in the discussion area on our Canvas site, and we'll deal with them right there very quickly, okay? Good luck, everybody.